Hi, in this video we'll introduce the Rabin-Karp's algorithm for finding all occurrences of a pattern in the text. At first, it will have the same running time as the naive algorithm from the previous video, but then we'll be able to improve it significantly for the practical purposes. So we need to compare our pattern to all substrings S of text T with length the same as the length of the pattern. And in the naive algorithm, we just did that by checking character by character whether pattern is equal to the corresponding substring. And the idea is we could use hashing to quickly compare P with substrings of T. So how to do that? Well, let's introduce some hash function h. And of course, if it is a deterministic hash function, and we see that the value of hash function on the pattern P is different from the value of this hash function on some string S, then definitely P is not equal to S, because H is deterministic. However, if the value of hash function on P is equal to the value of hash function on S, P can be equal to S, or it can be different from S if there is a collision. So to exactly check whether P is equal to S or not, we will need to call our function R=equal on P and S. And so this doesn't yet save us any time, but we hope that we could call this function R=equal less frequently because there will be only a few collisions. So we will use polynomial hashing family, calligraphic P with index P small, with some big prime number P. And if P pattern is not equal to S substring of text, then the probability that the value of the hash function on the pattern is the same as the value of the hash function on the substring is at most length of the pattern divided by our big prime number P. And we will choose a prime number P big enough so that this probability will be very small. So here is the code of our algorithm Rabin-Karp. It takes as input text T and pattern P. And it starts by initializing the hash function from polynomial family. We first choose a very big prime number P. We'll talk later about how to choose it, how big it should be. And we also choose a random number x between 1 and p minus 1. Choose the specific hash function from the polynomial family. And we initialize our list of positions where pattern occurs in text with an empty list. We also pre-compute the hash value of our pattern, and we call the polyhash function to do that. And then we again need to go through all possible starting positions of pattern in the text. So we go for I from 0 to difference of the length of text and pattern. And for each I, we take the substring starting in this position I and of length equal to the length of the pattern, which is T from I to I plus length of the pattern minus 1. And we compute the hash value of this substring. And then we look at the hash of the pattern and the hash of the substring. If they are different, then it means that definitely P is not equal to this substring, and so P doesn't occur in position I, and so we don't need to do anything in this iteration, so we just continue to the next iteration of the loop without calling R=equal. However, if hash values P hash and T hash are equal, then we need to check if it's true that P is really equal to the substring of T starting in position I, or it is just a collision of our hash function. And to do that, we make a call to R=equal and pass there the substring and the pattern. If R=equal returns true, it means that pattern is really equal to the corresponding substring of text, and then we append position I to our result, because pattern P occurs in position I in the text T. Otherwise, we just continue to the next iteration of our for loop. So this is more or less the same as naive algorithm, but we have an additional checking of hash value and so we're not always calling r equal. We're calling r equal either if p is equal to the corresponding substring of t or if there is a collision. Let's estimate the running time of this algorithm. So first we need to talk about false alarms. We'll call false alarm the event when p is compared with the substring of t from I to I plus length of p minus 1 compared inside the r equal procedure, but pattern p is actually not equal to this substring. So it is a false alarm in the sense that p doesn't occur in the text t starting from position I, but we still called the r equal function, and we need to go character by character through p and the substring to test that they're actually not equal. So the probability of false alarm, as we know from the previous lesson, is at most length of the pattern over prime number p, which we choose. So on average, the total number of false alarms will be the number of iterations of our for loop multiplied by this probability. And so this total number of false alarms can be made very small if we choose prime number p bigger than the product of length of the text and length of the pattern. Much bigger. So now let's estimate the running time of everything in our code except for calls to the r equal function. So the hash value of the pattern is computed in time big O of length of the pattern. Hash of the substring corresponding to the pattern is computed in the same big O of length of the pattern time, and this is done length of text minus length of the pattern plus 1 times, because that is the number of iterations of the for loop. So the total time to compute all those hash values is big O of length of text multiplied by length of the pattern. Now, what about the running time of all calls to r equal? Each call to r equal is computed in big O of length of the pattern, because we pass there 2 strings of length equal to length of the pattern. However, r equal is called only when the hash value of the pattern is the same as the hash value of the corresponding substring of t. And that means that either p occurs in position I in text t, or there was a false alarm. And by selecting the prime number to be very big, much bigger than the product of the length of text and the length of pattern, we can make the number of false alarms negligible, at least on average. So, if q is the number of times that pattern p is actually found in different positions in the text t, then the total time spent in r equal on average is big O of q, which is number of times p is really found, plus the fraction t minus p plus 1 multiplied by p and divided by prime p, which is the average number of times that a false alarm happens. So q plus number of false alarms is the number of times that we need to actually call function r equal. And then the time spent inside the function r equal is proportional to the length of the pattern. So totally this is the same as big O of q multiplied by the length of the pattern, because the second summand can be made really small, less than 1, if we choose big enough prime number p, and we only get the first summand multiplied by length of the pattern. And now the total running time of the Rabin-Karp's algorithm in this variant is big O of length of text multiplied by length of pattern plus q multiplied by length of pattern. But, of course, we know that the number of times that pattern occurs in text is not bigger than the number of characters in text, because there are only so many different positions where the pattern could start in text. So this sum is dominated by the summand big O of length of text multiplied by length of the pattern. So this is basically the same running time as our estimate for the naive algorithm. So we haven't improved anything yet, but this time can be improved for this algorithm with a clever trick, and you will learn it in the next video.